get started into this today. Now, we've talked about the graphical method. We're going to get into actually what's referred to as the simplex method, okay? And like I said, this was developed by a guy, his name was George Danzig in 1947. And it's a way to solve problems that have really two. You can solve it with two. That's what we're going to start off with. But it'll solve up to n decision variables. Okay? It's an iterative procedure that doesn't rely on trying to figure out where these lines and planes intersect one another. So it's a very straightforward procedure. Maybe not. Okay. So what I'm going to try to do with this problem is take a simple linear programming model and solve it using what's called the simplex method, and show you what's going on relating to the graphical method. So I have this company, Eager Beaver Woodworking Company. It's a small American woodworking shop. I've already gone over this problem actually of how to solve it. I think, yeah, we set it up graphically. Okay. So we essentially have this model that says we want to maximize 4x1 plus 3x2 subject to these two constraints. Okay? So first thing that we have to do is we have to rewrite this model in what we refer to as standard form. Now standard form means we got to get rid of these inequalities. Okay? And the way we get rid of these inequalities is we replace it with something that's called a slack variable. Okay? So what is a slack variable? Well, let's suppose that I have something that looks like, let's suppose that I have 2x2 or 2x1 less than 6. Okay? Less than or equal to 6. Okay, so, and let's suppose that we say that x1 has to be greater than or equal to 0. So if I just look at the integers for this, I mean there's an infinite number of solutions, but x1 would be equal to something like 1 would work, 2 would work. What am I doing? Three would work, or I mean you could even have like anywhere in between. So everyone agree that all of these values would work. It would satisfy this constraint, right? Okay. So now the problem is I've got this pesky inequality sign, and inequalities make the problem easier to work with in the long run, but they're really hard to work with in terms of trying to find. I mean, the answer is where regions intersect. So you get an infinite number of solutions. So what we do is we go in and we kind of swap out one level of complexity for another level of complexity. I go in and I create this new variable. I create what's called a slack variable. Okay. I'm going to call this guy S1. Okay. And I'm going to rewrite this equation as 2x1 minus s1 is equal to 6, where s1 has to be greater than or equal to 0. Okay? So I'm going to show you that this equation is equivalent to this inequality. Okay? So what I've done is I swapped out this guy for an equal to an equation which simplifies this problem. But in the process of swapping him out, I ended up having to subtract what's referred to as a slack variable. Okay, so how does this work? Well, let's go in and let's think about this just a moment. Okay, so if I plug in a value of x1 is being equal to 1, then what does s1 have to be equal to? So if x1 is equal to 1, what does s1 have to be equal to in order for this equation to be valid right here? Let's see, 2x1, yeah, have to be equal to -4, right? All right, now what happens if x1 is equal to 2? What does s1 have to be equal to? -2. Now if x1 is equal to 3, what does s1 have to be equal to? All right. Now, if x1 is equal to 4, what does s1 have to be equal to? 2. All right. Now here's your problem. Is s1 is equal to 2, right? Wait a minute. What did I just do here? I think I messed up. Did I say less than, minus? (2x less than 6), 2x minus 6. I picked a bad example. That's what I did. Two x1 is equal to 6. Yeah, I really picked a bad example. That was a bad example. It's on the right track. I just picked a bad example. Let's try something else. Let's just try what's in the book. 2x1 plus 3x2 is less than or equal to 18. 2x1 plus 3x2 is less than or equal to 18. I'm going to go in and rewrite this as 2x1 plus 3x2 minus s1 is equal to 18. Okay? Okay, so if I were to go in and pick, sorry about that, that was I should have used two variables because it's complicated what happened. It goes through the origin and it messed everything up. Okay, so if I pick, let's just start picking some numbers, some strategic numbers. Let's suppose I pick the value x1 is equal to 9, okay? Now what's x2 have to be equal to? x2 has to be equal to 0, right? And s1 would have to be equal to, well, let's suppose I pick these 2 points right here. x1 is equal to 9, x2 is equal to 0. s1 has to be equal to what? It has to be equal to 0, right? You agree with that? Agree with that? Okay. Now let's suppose that I pick, let's suppose I pick x1 is equal to 6. So that'd be 2 times 6 is 12. 6. x2, let's suppose equal to 2. So s2 has to be equal to what? I mean s1 has to be equal to what? It also has to be equal to 0. Would you agree with that? Right? Okay. Okay. Now let's go pick these values. x1 is equal to 6. x2 is equal to 1. So what does s1 have to be equal to now? Using this equation right here. It's going to be equal to what? Is it going to be equal to -3? Uh, so x1, or let's see, so you'd have 15 right here, right? So you'd have this value right here would be equal to 15, and then 15 minus what? -3. You were right. Makes this valid, right? Okay. But the problem is that -3 is actually violating this constraint right here. Okay? I got something weird going on here that's not making sense. Why is it doing that? One, two. So if I make that 3. Okay, so something's not jiving in my mind right now, but it doesn't mean it's wrong. Essentially, just for the time being, Thursday we'll go over this in more detail anyway. I just wanted to touch on it. Essentially, what I want you guys to accept, and I'll prove it to you on Thursday, is that this model right here, this guy right here, is equivalent to this guy right here. So the only thing I've done is I have gotten rid of these inequalities and I've replaced them by extra variables, okay? So I've given up one simplicity or complexity for another, all right? But we're going to see how the second model is actually simpler and what we can do with that on Thursday, okay? There was a bit of confusion in one of the problems, and I took a look at it and I figured out where the confusion came from. In the chapter that I have posted, I've changed it here, I just haven't reposted it. When I converted this problem to what's called standard form, I'd subtracted these S1, S2 variables. You're supposed to add them. I don't know why I had done that. Well, I'll show you what it's going to do, because I kept getting the wrong, it was on the wrong side. Yeah, and I couldn't figure out what was wrong. But sometimes you do add a variable, but they're called surplus variables, and you add a slack variable and subtract a surplus variable. And usually you use surplus variables when you're trying to minimize a function. And I just haven't had time. By the time I called it, I changed some of it, but I don't know what impact it's going to have on the mathematics. So I'll have to go through, and I don't think it'll have some, but not. Anyway, I'll go through another example. But the first thing I want to do is explain it. Okay? Yeah, go ahead. What I'm probably going to do, you noticed in the on the syllabus there was some projects. It's like 15% of your grade. What I plan on doing is giving you, after each exam, a small little project that's kind of a real-world problem that you work offline and kind of bring back the next class period or the next week. Yeah, it'll be problems that you can do in class, whereas the other ones you'll have to do using a computer. So it'll give you experience actually using the computer. Okay. So let's suppose that we had this function. Let's suppose it was 3x1 plus 2x2 is less than or equal to 12. Okay. So I said the way that we could rewrite this function would be 3x1 plus 2x2 and then plus s1 is equal to 12, where s1 is greater than or equal to 0, right? Okay, so I said let's start picking some numbers. So if I let x1 be equal to 0, then x2 is equal to what? It's going to be equal to 6, right? And then s1 would be equal to what? Be equal to 0. All right, let's go to the other extreme. Let's let x2 be equal to 0. x1 would be equal to what? 4. And s1 would be equal to 0, right? Okay, let's pick somewhere in between. Let's suppose we let x1 be equal to 1, x2 be equal to 2, and what does s1 now have to be equal to? So it's going to be 3 plus 4, so it has to be equal to 5. Okay? So in this particular case, notice that 5 does not violate this constraint. 5 has to be greater than or equal to 0. Okay, let's pick another problem, just real quick. Let's suppose that x1 is equal to 3 and x2 is equal to 4. So what's s1 has to be equal to? It's going to be 9 plus 8 is what? 17. It's going to be equal to negative 5. All right, now the problem is that this guy all of a sudden violated this constraint. Okay? So, big deal. Well, let's go in and see x1 is equal to 3 is 9. x2 is equal to 4, 8. 9 plus 8 is 17. But 17 has also violated this constraint right here, less than or equal to 12. Okay? And that's what I just, for some reason, couldn't get the other day, and it was simply because I was subtracting instead of adding. So my question is, does everyone see how this guy right here is equivalent to this guy? Is that clear to everyone? Okay. So essentially what we've done is we've turned this guy into this guy. All right? And that's important because this equation is a whole lot easier to work with than the inequality. Okay? Okay. Now, before we go any further, I always get in big trouble when I do this, but I'm going to try it anyway. Let's suppose I have x1 plus x2 is equal to 20, and 2x1 plus 3x2 is equal to, let's make this guy 10. Let's make this guy 26. All right. So what is this? This is two simultaneous equations, right? Now how do we go about solving this? Anyone know? Do it a couple ways. Let's do the first way, substitution. I'm going to say x1 is equal to 10 minus x2, right? You agree with that? Then wherever I see an x1, down here, I multiply 10 minus x2 plus 3x2 is equal to 26. So what do I get? 20 minus 2x2 plus 3x2 is equal to 26. I end up getting x2 is equal to 6. And then x1 will be equal to what? By looking at this guy right here, what would x1? It'd be equal to what? 4, right. So does everyone see how I solve this problem using substitution? No sweat, right? Now, you said we can do it another way. Another way we can do it, and I'm going to show you, this is going to be important here in just a minute. Because trust me, what I'm about to teach you, you're not going to get. No offense. It's just the way it is the first go around. Unless you happen to be a really good teacher like me, and then there's a slim possibility maybe. Yeah. Okay, so how could we solve this? Well, we can multiply this guy up here by negative 2, right? And so this would be negative 2, and then negative 20. and then we just add them up. We get 0x1 plus x2 is equal to 6. So x2 is equal to 6, x1 is equal to 4, right? No sweat. All right. Now, here's a point that I want you to make. I want you to get out of this. Does everyone see how substitution gives the exact same answer as adding these two equations, multiplying by a constant and adding the two equations? No problem there. Good? Alrighty then. Let's go in here and take a look at a problem. Now, and I posted these slides. They don't necessarily coincide with the book problems, but I need to fix those problems. But anyway, this will get the point across. Like I said, we're going to be talking about the simplex algorithm. Okay? Simplex algorithm is how we're going to solve these n-dimensional problems. So we saw in the model formulation and graphical analysis discussion, we can find the solutions to linear programming models using what's called the graphical method. But we can really only do 2 variables, 3 variables with a lot of work. Okay? So we need another method. So the method that we're going to use is called the simplex algorithm. And from the term algorithm, I think we can all see that this approach is a process. It's not just some simple formula that you plug into. Before we get into this, I'm going to talk about something. We're going to get to the basics, and we're going to be talking about standard form. Okay? So we got to understand what standard form is. Standard form, all you're trying to do is get rid of inequalities, all right? And you're having to give up something to gain something. So you're getting rid of an inequality, and you're adding a variable, okay? And I'm going to show you why that's important here in a moment. We're also going to be discussing something called basic variables and non-basic variables, okay? Now, most people that learn this simplex method, and I've taught a lot of people this method, most people that learn the method when I'm not teaching it, okay, like the way I learned it, I'm going to be honest with you, they really don't ever get what's going on. They just learn to plug and chug. But you go back and ask 90% of the people that took an OR course to explain the simplex to them. I've had colleagues that are 10 years older than me that, to be honest with you, I really don't know how this thing works. I know how to do it, I know how to get an answer, I know how to teach it, but the fundamentals, I don't really know how it works. Now, I wouldn't say any names, but this is true, okay? So I spent a lot of time trying to figure out how this works because I don't feel that I can teach something unless I completely understand it, and I'll understand it for a few days and then I'll forget and I'll think that I understand it and realize I didn't and then learn something new. But anyway, I understand it enough. I don't think I could have developed it. Let's put it like that, okay? So, basic and non-basic variables, what are they? Well, they're essentially all the variables in the problem. They include all of our decision variables, our x1, x2, x3, x4 variables, plus any slack variables that we create, s1, s2, s3, s4, okay? Now, which ones are basic and which ones are non-basic, okay? Well, that's what we decide. We decide this when we're working the problem. And then from this, we're then able to compute the solution to our model. Okay? Now, as a little example, let's suppose that I give you this problem. 2x plus 3y plus z is equal to 16. 3x plus 6y, this is a z, plus 2z is equal to 24. All right? How would we go about solving this problem? Yeah. Okay. So, do like this. It won't solve. Why won't it solve? Need 3 equations. All right. Now, I'm going to talk about a very nuanced topic that most people, most professors that teach it don't really know what it means. I have a colleague, a good friend of mine, teaches at another university, and one day he called me and was asking me about a problem. And he asked me about a topic called degrees of freedom He said, I'm teaching this in class. I do all the math, but I just don't quite understand what it means. Can you help me out? I said, yeah, I can help you out. It took me a while to figure it out, but it's a really simple concept. All right. I may have even talked about this in some of my electrical classes when I was trying to explain grades to you guys. Now, degrees of freedom. I have three numbers, three blanks, and I want you to fill them in with numbers. Okay? So pick me a number, the first one. Make it reasonable. Just pick a number, 1 to 10. Just 7. Okay. All right, pick another number. 3. And pick another number. Just 5. All right, 7, 3, 5. Now, you picked three numbers. There was three blanks. That means you have 3 degrees of freedom, meaning you're free, or the problem is free, to accept any input you want. All right, now we'll try this again. Okay. Pick me a number. First number. 2. All right, pick the second number. 9. All right, what's the third number? Why? Well, you have 2 degrees of freedom, but one of these is already defined for you by the problem. Okay? So, by me giving you a little bit of information that the sum of these have to actually equal a number, what I did is I took away a degree of freedom from you. All right? You no longer have a choice over all 3 of those numbers. You can only pick 2 numbers. The other one, as soon as you pick 2, the other one is already predefined. Well, something similar happens up here like this. What you end up getting is these 2 numbers right here, you can pick all you want. So just like x plus y is equal to 5. Okay? You can pick 1 and 9, 2 and 8, 3 and 7, or an infinite number of combinations if you use decimal numbers, right? Okay? Now, so there are too many degrees of freedom in this problem up here. Okay? And that's why you need another, just like when I gave you this guy, okay? When I gave you this guy, I reduced the degrees of freedom. Okay, I reduced the degrees of freedom down to 2 degrees of freedom. All right. Now I can come in and give you another number. Okay, another metric. It's called standard deviation, and it'll reduce it even further. And I can come in and give you what's called a third moment of these 3 numbers, the distribution, and then all of a sudden all 3 are defined for you. There's only one possible combination. Well, that's why you need to add another equation. All right. That's why we need to add another equation. Okay. What happens if you don't have another equation? Well, that's where this guy was very smart to come up with this. Because these problems, actually, a lot of them, they don't have another equation. Okay? So, like I said, we may find that we have an infinite number of solutions to our model, and a lot of times this is often the case, and we'd like to find the best answer of those infinite number of solutions. All right, but now to get started, we must first choose which variables are going to be basic and which variables are going to be non-basic. Okay? So we'll set all the non-basic variables equal to 0 and solve for the values of the basic variables. Okay? So anytime you hear the word non-basic variable, all that means is the variable is currently set to 0. You've zeroed it out. You forced it to be 0. Basic variable may have a value of 0, but probably not. It can have any value required to solve the problem. So let's take a look at a problem. We have these 2 equations and 3 variables. So x1 plus x2 is equal to 3, negative x2 plus x3 is equal to negative 1. How do we solve for x1, x2, and x3? The answer is we can't. All right, there's an infinite number of solutions. But let's suppose that we look at what happens when we start to set basic and non-basic variables in the problem. So basically, In this particular problem, we have one basic variable in the problem. And the rule is we have n minus m non-basic variables in the problem, where n is the number of variables and m is the number of equations. Okay? Now, this is all under the assumption that the variables are linearly independent. And when I mean linearly independent, I mean this. 2x plus 3y is equal to 10. 4x plus 6y, that's a 10, is equal to 20. So how do I solve this? I can't solve it, because they're not independent. One's just a multiple of another. Alright, so you see if I multiply this guy by negative 2, I get negative 4x minus 6y minus equals negative 20. Cancel, cancel, cancel. You get 0 equals 0. No solution. There's an infinite number of solutions, okay? So you don't have any added information. You just multiply your equation by a constant. So that's what I mean when I say the term linearly independent, okay? Hopefully this will all come together in just a moment. Okay. So what we're going to do is we're going to decide what variables will be non-basic variable. Now once we decide this, we're going to set them equal to 0 and solve for the remaining 2. So what I'm going to do in this problem is I'm going to come in and I'm going to say, all right, x3 is going to be our non-basic variable. All right, why? Well, I just decided it's going to be. Okay, so I plug in x3 is equal to 0. Now all of a sudden I can solve for x1 and x2, right? I've gotten rid of this x3 right here. All right, so x2 is just equal negative x2 is equal to 1. So this means x1 is going to be equal to 2, right? Or I can go in and I can set x1 equal to 0. All right, then when I do that, x2 is equal to 3, x3 is equal to 2, or I can go in and set x2 equal to 0. So what's this tell us? Well, basically nothing at this point. We just need to understand exactly what a basic and a non-basic variable is. So a basic variable is essentially a variable that you're using to solve the problem. A non-basic variable is just the variable you set equal to 0. All right? Alrighty, so let's suppose that we have the following example here. 4x1 plus 3x2, x1 plus x2 is less than 40, 2x1 plus x2 is less than 60, and then both of them have to be non-negative. Okay? Now, remember from the last lecture, this is what we would do. We would simply go in and to get rid of that inequality. Well, let's go back here in just a moment. Let's take a look right here at these two guys. Now, suppose that just for a moment that these guys said this. Our problem would be solved, would it not? You just go in and solve for x1 and x2, put those variables back in up here, and you're good to go. You just solved the problem. But it wasn't. We had this. And we said inequalities don't work well. So to get rid of that inequality, we had to add these two guys. But we made up for it by making these two non-negative. But when we did that, what just happened? All of a sudden, I took two equations, and now I have what? 4 unknowns. x1, x2, s1, s2. So I've kind of shot myself in the foot. All right, if I could just get rid of that equation, or inequality, no problem. But I can't. I got to add another variable. Well, as soon as I add that other variable, now the problem, it has an infinite number of solutions. Well, it turns out that there are an infinite number of solutions to this. You know, I mean, that's the reality. You got two regions, and all the number of points in those regions are actually a solution. But we're trying to get this guy right here, the best guy. Okay, so what do? Let's go in and take a look at a graph of this model. Okay, so one of these constraints, let's see, 40 and 40 would be this guy. The other one would be this guy. So the 40 and 40 would be this guy and this guy. Just hold off on the slack variables just a moment because we're dealing with a region, right? So the intersection of these two regions would be right here. So if we look at all the points of interest, A crosses the x-axis, B crosses the y-axis, C crosses the x-axis, D crosses the y-axis, E is where the two cross, and F is where the origin is. So we've really got 1, 2, 3, 4, 5, 6. 6 real points of interest. Okay? So let's look at all the possibilities of our non-basic and basic variables. How many would there be? Well, we have two basic variables, and we have two non-basic variables, because remember the equation is n minus m, where n is the number of variables and m is the number of equations. So let's calculate the possibility, or the number of possibilities for doing this. Well, I'm sure all you guys remember this formula, right? I mean, that just come right to your mind when I mention that, right? Basically, here's what I'm saying. You got 4 colored balls, and you want to organize them 2 at a time. What are all the possible combinations? Have you guys ever had any classes in probability and statistics? You ever had to take any of those? No? Okay. Well, this formula gives you the answer. And it turns out that there's 6 possibilities. So if I have a red ball, a green ball, a blue ball, and a yellow ball, and I say, all right, take these balls out 2 at a time, but I want to know all the possible combinations, well, you just plug into this formula right here. So the answer would simply be 4 factorial divided by 2 factorial times 2 factorial on the bottom. So does anyone remember what factorial is? Exactly. So up here on top you got 4 times 3 times 2 times 1. Down on the bottom you got 2 times 1 and then 2 times 1. Well, the 1's don't really matter, right? So what you're left with is this. 4 times 3 on top, which is 12 divided by 2, gives 6. Everyone see that? Just a simple formula. You don't have to derive it, just know it. Okay? So this tells you all the possible combinations of taking 2 variables kind of at a time out of the total of these 6 variables. So you're probably like, well, who cares? I mean, okay. Well, here are those 6 possible combinations. I can either have, you can look at it either way, but let's just look at basic variables. So I can either have x1 and x2 as basic variables, x1 and s1 as basic variables, x1, s2 as basic variables, and by default that means that what is remaining is our non-basic variables. Okay? So, a non-basic variable, we said what? Those are variables that are equal to 0. Right? Okay. So let's go in and set our non-basic variables equal to 0. And then we're simply going to go in and solve for what our basic variables would be. Okay? So if I were to actually go in and set S1 and S2, remember I told you guys a minute ago, I'm almost set right here. Very close. Okay? So if I could set these guys right here equal to 0, now this what just happened? This became super simple to solve, right? So x1 and x2 are both equal to 20. Everyone agree with that? Well, you could go in and solve it, but you agree that they're both equal to 20, right? Okay. So, look what I got. I got x1, x2 is equal to 20. Well, let's go in for a moment and set x2, s2 equal to 0. Okay? So, x2, s2. So what? What do I do now? Well, I still only have 2 variables, so we know that x1 down here, from this guy, is going to be equal to 30, and s1 is equal to 10. Does everyone agree with me on that? Got it? Now, do you see what I'm doing? Here's what I'm doing. I'm getting rid of the number of variables I need to get rid of in order to solve these set of equations. And the easiest way to get rid of a variable is to make it 0. Because once you make it 0, it falls out of the equation, right? So if I have 4 unknowns, 4 variables, and 2 equations, it's like, well, you got 2 variables too many. No big deal. What will I do? I'll just go in and zero those guys out. All right? Then I can solve for the solutions. Okay. So who cares? Big deal. Why are we doing this? All right. So I went in and looked at all 6 possible combinations. All right. Now, here's what I do. I go in just for the heck of it, and I say, I wonder if there's any relationship between these solutions and those corner points. Remember we said corner points were important? Remember when I said that? Because corner point is kind of way up in the field where the 2 fences intersect and you're holding your GPS trying to maximize your elevation. It's going to be right on that corner point. So let's see if there's a relationship. Okay, x1, x2 is equal to 20. Huh, that's point E. All right, well, how about x1, x2 equal to 0? x1 equal to 30, x2 equal to 0. So x1 equal to 30, x2 equal to 0. Huh, that's point C. All right, look at this one right here. Well, we can't really look at this one because we violated a constraint. That constraint is S2 is equal to negative 20. Well, we don't even deal with it because we said it can't be negative, so don't even have to worry about it. This guy right here, he's negative 20. We don't worry about it. All right, let's go and say, well, how about when x1 and s2 are equal to 0, x2 and s2 are equal to 40 and 20. So x1 is equal to 0, x2 is equal to 40. Huh, point B. All right, x1, x2 both equal to 0 down here in the origin, point F. So do you see what just happened? That little trick of swapping out these variables to make some of them equal to 0 and solving for the remaining ones just listed all the ones that were feasible, just listed all of the points on the polytope. So we have 1, 2, 3, 4 points on the polytope. So, a little while ago, a few days ago, we would have had to go in and solve for each one of these, see where they intersect, get those the corner points that way. Now all we have to do is this little trick of going in, calculating all the possibilities, and seeing what's valid, and there are magically all the corner points on your polytope. Okay? So imagine that you got this big n-dimensional, say even 3-dimensional polytope, where you got planes coming, intersecting, and then the lines intersecting with the planes. I mean, that would be an absolute disaster trying to find those corner point solutions. We actually did that. I mean, disaster. But what this method does is say, no big deal. No big deal. You got 3 decision variables. Let's suppose you got 3 constraints. You're going to have to add 3 slack variables. So now you got 3 decision variables, 3 slack variables. So we got x's, got 3, s's, we got 3. So what's the equation? It's going to be a total of 6 factorial over 3 factorial times 3 factorial. So it's 6 times 5 times 4 times 3 times 2 times 1, 3 times 2 times 1. Well, these guys cancel out. 6 times 3, or 3 times 3 times 2 times 1. So this guy turns into a 2. This guy turns into a 2. So we got 2 times 2 is 4 times 5. We got 20. Okay? So that would have been a disaster trying to solve for all of those. Okay? But all you have to do is go in, and there's a very, very easy algorithm that gives you all those possible combinations. So instead of you having to go in and do that, remember how you would solve it? You had to use matrix algebra, take the inverses, and that's how you get each point. Now all you'd have to do is just go in and say, well, x1, x2, x3, all right? And then let all of our s's be equal to 0, then x1, x2, or say s1, like this, and just look at all 20 points, all right? And they would all be a corner point solution. Some of them would be feasible. Some of them would not be because of this right here. All right?
So, where you say you got 3 slack variables, but here you only got like x1 and x2.
Now that was just kind of hypothetical. Suppose that I had 3 decision variables and 3 equations. Then I would have 6 total variables, right? Because I'd had to add 3 slack variables to get rid of those inequalities. So that was kind of a hypothetical problem. Does that make sense? So the number of corner point solutions would have gone from 6 to 20. All right? But my whole point is this, is slowly we're starting to whittle away at this problem, make it more tractable. Okay? It's like, well, this still doesn't seem all that easy to me. Well, if you remember when I solved that 3-dimensional problem, all them planes coming together, remember for each point I had to take a 3x3 matrix, take the inverse, multiply, and I mean, that is not easy, especially if you were doing it by hand. And then figuring out what planes crossed where to even get that matrix is hard. What I have essentially done now is this. I have said, all right, there is a formula. There's a formula. We're not going to go over it because we're not going to use it. But I'm just trying to whittle away at this. But there's a formula that actually, if you plug in, well, I mean, it's really simple. Let's suppose that I give you, faster. You know, if I give you a red, a green, a blue, a yellow, a purple, and an orange jelly bean, okay? And I say, I want you to do them 3 at a time. How many possibilities? Well, the equation is n divided by k factorial times n minus k factorial, where n is the total and k is, say, the number of unique. You know, the number of ways you want to separate. I mean, this is the formula. You don't have to go in and reprove it or anything. It's as simple as that. Very simple formula. Well, then there's a simple algorithm that would go in and actually list all 20 of these, okay? I don't know what it is off the top of my head. But my whole point is, if you had that algorithm and I give you all these decision variables, it's going to go in and tell you, okay, well, here's all the possible combinations. It's 6 taken 3 at a time. And then just set the other 3 equal to 0. And now you can solve them for the remaining 3. And these are your corner point solutions. All right? And if you find one that's negative, just disregard it. But those other points are going to be on the corner point of this polytope. So then all you have to go in and do is see which one is larger. All right? So you see how the problem's starting to become a little simpler. Still not quite there yet. So the whole point behind this is this, that there is a purpose for slack variables. And the slack variables, all they do is get rid of inequalities. That's it. All right? The problem is they add more variables to the problem. But the way you take care of it is you simply set them equal to 0. Because as soon as you set them equal to 0, they disappear. All right? Does that make sense to everyone? Okay. Well, let's move on to the next presentation then, since that makes sense to everyone. Okay. So here's what we got. We got a furniture company. This is a little different than the other furniture company, but it's still a furniture company. What is wrong with this? All right, we got us a furniture company. Okay. So here's what we got. It's a little different than the other one that we had, but it'll serve the purpose. We've got a company that makes desks, tables, and chairs. All right, we got 3 resources: lumber, finishing hours, and carpentry hours. All right, here's how much resources each one of these takes. Takes 8 board foot for a desk, 6 for a table, 1 for a chair. All right. Now the question is, how many tables, desks, and chairs should we build? Well, we don't know yet, because I have to tell you how much profit we're making off of them. So these aren't quite as good as the last ones. But let's suppose we get $60 profit off a desk, $30 off a table, and $20 off a chair. Okay? So essentially, our profit equation, does everyone agree that it's going to be Z times 60x1 plus 30x2 plus 20x3? Based on x1, x2, and x3 being the number of tables, chairs, and desks I'm selling? All right, no problem there. All right. Now we believe that we can't sell any more than, say, 5 tables a month. So what would the model look like? All right. Well, here are how many board feet of lumber we have, say, per day, week, whatever it is. This is how much time we have allocated for finishing hours, and this is how much time we have allocated for carpentry hours. So my complete linear programming model will be this guy right here. I want to maximize my objective function, which is 60x1 plus 30x2 plus 20x3, subject to these. Now I have essentially 4 constraints. All of these are kind of my resource constraints. And then this is a demand, saying, well, you can't sell more than 5 because the market won't allow it. And these are my non-negativity. Okay? So far, so good. No problem there. Any question on that? Good. A question or no?
Yeah, I do.
Okay.
I like the hours being split up.
The hours?
Yeah.
Well, I said that you have 20 finishing hours and 8 carpentry hours.
But there's something probably negative specified how long each one is.
Yes. It was right here. Right here. So it takes me 4 finishing hours to complete a desk and 2 carpentry hours to complete a desk. 2 finishing hours for a table, 1.5 carpentry hours. So this is kind of your information matrix. So you got that? Is that clear? So these guys are simply the coefficients in our model for our constraints right here. Clear? Everything's good. All right. All right, so we talked earlier about something in standard form. Well, this is really in standard form. Here's what we do. We have Z equal to this. But what we're going to do is just pull everything over on this side of the equation, just for simplicity. So all we did was just pull all of these over. They were over here, and we moved them over here. All right? So they all become negative. That's clear, right? No issues about that. And we're just doing this. It just helps in terms of simplicity. So this way, on this side of the equation, we get constants. And over here, we simply have equations, right? So, how many total variables do I have? I have 7, right? 7 total variables. How many decision variables do I have? I have 3, all right? How many equations do I have? I have 4, okay? So the question is, we have 7 unknowns and 4 equations. So we got 3 variables too many, all right? We have essentially 3 non-basic variables, okay? Now, here's what we're going to do. We're going to start off, and we're going to say, you know what? Which variables should be our non-basic variables? Let's just start off with our decision variables, because we're not making anything anyway. Let's just let our decision variables be set equal to 0. All right? Now, as soon as we set our decision variables equal to 0, what happens? Well, everything that's got an x in it just falls out. You agree with that? And what we're left with is that Z is equal to 0, making no profit. We got S1 is equal to 48. We got 48 board foot left over. S2 is equal to 20. That means we've got, 20 carpentry hours left. Haven't used anything. 8 finishing hours left and 5 of our demand. So, I want you to start gaining a little bit of insights. These slack variables, actually, it turns out they're going to help us out. They're going to tell us something. It tells me if I'm not making anything right now, that whatever my slack variables are equal to is how much I got left of something. Okay? Well, right now it's simple. No problem. No sweat. So it got everything you started with because you've not made anything. Okay? So, let's suppose we set Z as a basic variable, just for the time being, because we're going to be solving for him too. So let's just go ahead. Might as well. Let's throw him on. We got all kinds of variables we're fooling with. Just one more is not going to matter. Our non-basic variables are x1, x2, and x3. All right? Now, we can see that if we're not making anything, we're not making any money. Nothing intuitive there. Okay. Now we have a solution to the problem. It's not just any solution. It's called a basic feasible solution because it's in a corner point. It's over here in the corner here at the origin. All right? So it's important to us. Okay? Now, basic feasible solutions are those solutions that are on the corner point. Sometimes they're called corner point solutions. Usually refer to them as basic feasible solutions. So I think we can all see that we're not near the optimal solution yet because the profit is equal to 0. So now we need to find a better basic feasible solution. So how are we going to do this? Well, one possibility is plugging into that equation I gave you that you would learn, say, if you took a probability course, and plug it into an algorithm and listing ever how many combinations. We got 7, taking 3 at a time. So it'd be 7 factorial divided by 3 factorial times 4 factorial. Okay? So whatever this number is, I don't know what this number is, but it's going to be pretty big. It's going to be 7 times 6 times 5. 6 times 5 is 30. 10 divided by 6 divided by 3 would be 70. 35. So there'd be 35 possibilities. So that'd be one way to do it. And just say, well, I found one. All right, was it better and worse than the last one? Well, let me plug it in. It's better. But the problem is you'd still have to go through all 35. Well, 35 is better than infinity. I'll give you that. Okay? So I'd rather go through 35 possible combinations than an infinite number. So with the last technique I showed you guys, you took an infinite number of solutions and narrowed it down to 35. So that's pretty good. But what I'd like to be able to do is take 35 and maybe narrow it down to 3, if possible. All right? And it turns out it is possible. All right. So here's what we're going to do. We need to start changing the decision variables, x1 and x2 and x3, until we get a better solution. The question is, which one should we change? All right. Now, here's what I want you to think about, just for a moment. First day of the semester, I came in, I gave you this problem. You had no idea how to solve it. What would you probably do? Yeah, well, you'd probably go in and say, well, you know what, it seems that we make the most off a desk. All right, so let's just see how many desks we can make. We'll let the other two slide. The problem seems a bit complicated. So, you know what, let's just max out and make all desks. If that's possible, let's go for it. So let's go in and see how many desks we can make. Okay, so what you do is you start increasing the number of desks you can make. Okay, now, we'll change x1 to some other variable other than 0. So as soon as we do this, x1 is no longer a non-basic variable because it's no longer equal to 0. Now, for this reason, we call it an entering basic variable. It was set equal to 0. Now it's going to be something else. So it is becoming a basic variable. Okay? Now, what happens if two variables increase at the same rate? So what would have happened if we'd have had 60x1 plus 60x2? Well, we just picked one. Just, I don't care. Pick x1 or x2. It doesn't matter. Okay? Now, the question is, how large can we make x1? Well, the size of x1 is dependent upon our resources. Okay? So, we have to go in down here and we do what's called a ratio test. Okay? So if we look at the first constraint, just the first constraint alone, which is what? Labor or board feet. So how many desks can you make from 48 board feet? Well, would everyone agree that it's 6? Got 48 board feet. It takes 8 board feet for each desk. 48 divided by 8, 6. Right? How many can you make from your 20 carpentry hours? Well, you got 20 carpentry hours. No, finish hours. 20 finishing hours. Takes 4 hours a desk. That means you can make 5 of them, right? And 4 carpentry hours, you can make 4. Now this last one down here is no limit because we're dealing with X2. It says you can't sell more than 5 tables. Well, I'm not talking about tables. I'm talking about desks, so you can sell 1,000,000 of them if you want, okay? So what we do is we go in and we say, well, the maximum number we can make based on all of our constraints would be 4. All right? Because kind of 4 is kind of like the smallest of the smallest. All right? So the analogy is the winner of the ratio test would be something like, I give you 3 rules. You have to stay in the U.S., you have to stay in the state of Virginia, and you have to stay in the Hampton Roads area in Virginia. All right? Well, these other 2 are really kind of redundant. You don't need them. Because if I tell you got to be in the Hampton Roads area, you have to be in the Bluefield area. I didn't need to tell you got to, well, in Bluefield, you got Virginia and West Virginia, but pick another, Roanoke. You got to stay in Roanoke. Well, I don't tell you need to stay in Virginia, because if you're in Roanoke, you're in Virginia. And if you're in Virginia, I don't have to say, well, you can't go outside of the country. Take your passport, something like that. All right. So, do you see how those other 2 constraints become redundant? So we only have to deal. What we're doing is we're trying to whittle this problem away to where instead of looking at it as this great big problem, you keep going. It's like, oh, so I'm just dealing with an equation, right? Yeah, okay. Well, that's easy. Okay. So I think it can clearly be seen that x1 must become a basic variable in row 3. Okay? This guy right here. This is where we're actually going to make x1 become a basic variable. So, if x1 becomes 4, okay, these guys are still 0. This guy's still 0. This guy can change. But if we make this guy 4, he becomes 8, right? As soon as we make him 8, what does this guy become? He becomes 0. All right? So when we make S3 0, what exactly did this mean? Well, in reality, what it meant was we used all of that resource. So we had 8 finishing hours available, right? Well, we spent all 8 of them making desk. So S3 now, when it goes to 0, that actually tells me, guess what, buddy? You used all your finishing hours. You can't use it for anything else. So that's what it really means, okay, in words. That S3 is actually telling you what's referred to as a slack variable, how much stuff you got left over. Did you use it all? Well, it turns out we did use it all. And that's our whole point. We want to use it all for this particular constraint. We want to max out, okay? Now, he became 0. So as soon as he became 0, what did he become? What would we call him now? A non-basic variable, right? But x1 was a non-basic variable. He became a basic variable, so we called him an entering basic variable. This guy was a basic variable, and now he became a non-basic variable. So guess what we're going to call him? We're going to call him a leaving basic variable because he became a non-basic variable. So, is it somewhat intuitive that what all I did was I swapped out x1, he was 0, and I traded him out for s3, and now he became 0. They kind of swapped in a way. that kind of somewhat intuitive? But guess what? I still got the same number of non-basic variables. I still got the same number of zeros that I can plug into this whole model and have the same number of equations as I do decision variables. Okay? So, now we must always make the entering basic variable in a row that wins the ratio test. In this particular case, this guy was row 3. And we know why it was row 3, because the most you can make was 4 out of row 3, okay? Now what we would ultimately like to do is make the coefficient in front of x1 0 in all rows except the row that wins the winner of the ratio test, okay? And in that row, we'd like to make the coefficient 1. So what does that mean? Well, let's take a look and see. Let's suppose I go back over here, and I say we have x plus y is equal to 10, 2x plus 3y is equal to 26. All right. Now, go back in. Let's just do substitution for the heck of it. I'm going to say x is equal to 10 plus 10 minus y. 10 minus y. All right, so then I say 2 times 10 minus y plus 3y is equal to 26. Now, what happened to x in here? Poof, he disappeared, right? He's gone. So essentially, he's still in the model, but he's just 0x. All right? Would you agree that that's the same? All right. Now, when I go in and I solve this, I get 20 minus 2y plus 3y is equal to 26. So I got y is equal to 6. What's the coefficient in front of y? 1. What if I'd have had something like 2y is equal to 12? What would I have done? Divide it out by 2. All right? So what I'm really trying to do when I solve these equations, whether you know it or not, is you're trying to get a coefficient of 1 in front of the variable of interest, which would be y, and you're trying to get a coefficient of 0 in the other variable, which is x. All right? So that's what we're really trying to do, even if we were to do it the other way, where we multiplied this guy times negative 2. Negative 2x minus 2y equals negative 20. What I'm really trying to do is get 0x plus y is equal to 6. So ultimately, I'm trying to get a 0 in front of this guy and a 1 in front of this guy. All right? Do you see, in reality, that's what you're really trying to do? That makes sense? Okay. So, we don't want to get rid of x1 of all of our equations. Just we want to leave one equation that has x1 in it, just like I had y equals 6, because that's going to tell us the value of x1. And the other equations, what we're trying to do is actually get rid of x1. So essentially, we're trying to rewrite our constraints in terms of our remaining decision variables. Okay? And let me do one little example on this. So let's suppose that I had x plus y plus z, and this is no way it's going to work out, but I don't care. It's equal to 12, 2x plus 3y plus 4z is equal to 40, and then 5x plus y plus 2z is equal to 25. All right? So how would I go about solving this? Well, I'll probably use a matrix, but I could use substitution. I could go in and say, well, x is equal to 12 minus y minus z, right? And then I say 2 times 12 minus y minus z plus 3y plus 4z is equal to 40. And then 5 times 12 minus y minus z plus y plus 2z is equal to 25, right? That's what I would do. I'd go in and rewrite it. But let me ask you this question. What happened to the coefficient in front of x in these two equations? What happened to x? Poof, it disappeared, right? So what I'm trying to do, essentially, I'm trying to get rid of this guy, get rid of him, you know. And then I can do it again with y and z. It's like, get rid of him just for a minute. I'll come back and solve for him later. I'll plug and chug. But I want rid of him. He's causing too many problems. Just get him out of here, okay? So that's what we're really trying to do, right? You're trying to get rid of him in these other two equations. So essentially, you want 0x plus this and 0x plus this. And then here you want a 1x, because 1x is going to actually tell you, when you figure out what y and z, what the values are. That makes sense. You want one equation that has a 1 in front of the coefficient of the variable of interest, and all the rest of the equations you just want to get rid of them so they don't mess you up. Okay? Everyone clear on this? All right? But we need to keep one equation that contains x1, because this is going to give us the answer to what that guy actually... Okay. So let's take a look at row 3, because this is the row that we used to exhaust or get rid of x1. So in row 3, we had this guy. All right? Now how do we get a coefficient in front of this guy? A coefficient of 1. Well, all we have to do is divide out by 2, right? Now, as soon as we divide out by 2, this is what we get. So we could actually rewrite this if we wanted. We could say x1 is equal to 4 minus 0.75 x2 plus 0.25 x3 minus 0.25 x3 minus 0.25 x3 minus 0.5 s3, right? So we're right back to where we were just a moment ago, okay? So that's how we get a coefficient of 1 in front of x1, the variable of interest. I simply just divide out by the coefficient in front of that variable, right? So not rocket science. Good? All right. Now how do we get rid of x1 and all these other equations? And how would we do that? Well, what we would simply do is we would go in and take this guy right here, and every time we saw an x1, we'd just sub him in. So do you agree that if we subbed x1 into all of our other equations, that if we subbed x1 with this guy, then in all of our other equations where there used to be an x1, he would disappear? Does everyone agree with that? He'd disappear. Okay? So here's what we did. We got rid of x1 out of our whole model except just one little equation. All right? So if we went in and subbed in row 0, row 1, row 2, and row 4, not row 3, because row 3 is where we decided we're going to manipulate x1, that we could rewrite them in terms of the other variables that didn't include x1. Would you agree with that? So originally, here's what we had. We had x1 right here, 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 and we didn't have one here, so it didn't matter. But we want to keep him here because he is the row that allowed us to do everything. Everywhere else, we want to get rid of him. Okay? So whenever we see an x1, we plug something in. We plug this function in. And when we plug that function in, here's what we get. Okay? So we'll go back in. We don't have time today, but I'll go in and show you how to do it. But what I want you to realize is, look, in row 1, do you see an x1? Nope, he's gone. In row 2, do you see an x1? Nope, he's gone. How about row 3? Nope. How about row 4? Yep, row 4 we do. But we wanted to keep one, just like we do when we're subbing it out. You always have to keep x1 equals something, because when you figure or x equals something, because when you finally figure out what y and z are, you got to plug back in to get the value of x1. And row 4, nope. So the whole point is to get rid of a variable in your whole model except one equation. All right? And I'm going to sum it up by saying, what was the value of x1? What did we say that value was when we solved? It was 4, right? Everyone remember that? That it took, we had, 8 finishing hours available, and it took 2 finishing hours for each one, so you can make 4 of them based on the third constraint. All right, we make 4 of them. They cost $60 a piece. How much money did we make? $240. Well, what number do I see right here? 240, right? Okay. So we said, do you see how this is starting to work? Magically, it's starting to give us an answer. Now, what are our non-basic variables? Our non-basic variables are still x1. No, not x1. They are x2, x3, and s3. Because we swapped out this s3 right here for an x1. So let's go in and start plugging in. Let me see. Yeah. So let's go in and start plugging in zeros for S1, X2, S3. So this guy disappears, 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 this guy disappears, right? So do you see when I plug in all of those zeros, look what I'm left with. That. Not even left with equations. I'm left with numbers. All right, so my x1 is equal to, look, it even tells me right here, x1 is equal to 4, making 4 desks. So if I make 4 desks, how much money do I make? $240. All right. Now each desk took how many board feet to make? Anyone remember that? Took 8 board feet to make. All right? 8 board feet to make. All right, so if I take 4 desks, they each take 8 board feet to make, how many board feet did he use? 32. How many did I originally have? 48. I used 32 of them. Huh. Look, I'm left with 16. Look what this guy says. S1 equals 16. Well, S1's the slack for the number of board feet. So this number actually tells me now how much I have left over. S2 is equal to 4. This is how many finishing hours, I think. How many carpentry hours do I have left over? Right here. S3 equal to 0. Used them all. And how many of my labor or my demand do I have? Still all 5 because I didn't make any tables. All right? Clear? Now am I finished? Well, let's go. I'm going to stop here in just a moment. This was our original profit equation. And I went in, substituted out. Now look what I got. New profit equation. Now, if I make tables, what happens to my profit equation? What happens to my profit according to this equation if I make a table? Goes down. So would I want to make a table? Probably not. How about if I make a chair? What happens to my profit? Goes up. So I'm going to go in and say, you know what? Maybe I ought to look and start making some chairs. See what happens. Okay? And essentially, this is where the iterative part of the procedure comes into play. Now I just look at it as a brand new problem. I've got a new model. All right? So I go in and say, well, a moment ago I picked X1 to enter. Now I'm probably going to pick X3. And then I resolve it just the way I did, and I'm going to hopefully get a better answer. And we're going to find that it only takes us 2 iterations. 2 iterations, and we find the optimal solution to this problem. All right? Now,
versus like
Well, when you say I forget I solved for, I just essentially have this new model. Okay? So essentially, this is, I'll say, this guy right here becomes my new model. All right? Well, that's where the magic occurs. Because what happens is, like what you said, it's like, well, you can't make anything else because you don't have any hours left, right? Well, the magic occurs that on the next iteration, it automatically will subtract a little bit from x1, and it'll make up for it with x3. And you won't even know it's happening. So you go from having an infinite number of possibilities down to 35, which is a pretty good increase, down to essentially 1, 2 iterations, and you got an optimal solution. And that's why this methodology, algorithm, can solve a problem that has 100,000 decision variables, because it may only take 100 iterations to solve a problem like that. Okay? So, is it becoming clearer what's going on? It's so simple, I'm embarrassed to even teach this stuff. You know? Got it? Alright, well, I'll meet you guys then on Tuesday, and we'll finish up this topic. Okay, before we get started, we're going to finish up today basically Chapter 3, Module 3. Shouldn't take just a couple minutes to finish that up. Then we'll go into Module 4, which is how to use the computer to solve these problems, so that won't take long. So, after Module 4, we're supposed to be having an exam. So what I'll do is I'll give you guys some homework. I'll post that today, and I'll come in on Thursday and we'll go over the homework, okay? And then next Tuesday we'll have an exam. Does that sound reasonable? Okay. So what I'm going to do with this exam is the in-class exam. I have to make it where you guys can work it in class, okay? I don't really like that because I think that to learn this material, you need to really do like realistic size problems. But nonetheless, that's how we'll do it. So what I'll do is I'll give you guys an in-class exam. And then you notice how in the syllabus I had like 15% for a project. What I'm going to do is after each exam, I'm going to give you guys one problem, okay, where you need to go out and use the computer and solve that problem. And that's going to count as like a mini project. And that'll be worth 5% of your grade. So it won't count towards your exam. Your exam will be a separate grade, your project grade, but it'll still be a significant amount. I mean, 5%, that's a significant assignment. And the reason why I want to do this is to give you guys some experience as to actually solving one of these using the computer. We don't really have the facilities, and we're just not set up to do an exam like that, where you guys come in, have a computer in front of you, and solve it real time. We just don't have those facilities. So that's how we're going to go about doing that. All right. So like I said, I'll go over on Thursday homework problems for Chapter 3 and Chapter 4, and answer any questions you may have. And then the exam next Tuesday will cover essentially Chapters 1 through 4. Okay. And I'll give you guys some idea of what to expect on next Tuesday. And also, if you got any friends that's in here and you don't see them, you might want to tell them that we're having an exam.
They'll be here in like 20 minutes probably.
Okay.
That's the normal.
Okay. So we'll be having an exam. So kind of a week heads up. So if they don't show up, like well, maybe they'll get a 5% on the project, but the exam's going to be 0. Okay. All right. So iteration 1. Remember what we'd done with iteration 1 for this problem? We essentially had replaced, we'd taken one of our non-basic variables, which we start off with basically all your decision variables, x1, x2, and x3. You set them all equal to 0, and then you simply swap out one of your decision variables with one of your slack variables that is usually non-zero. So your slack variable just represented how much excess you have of something. And you go in and you essentially swap them out, okay? And in the process of doing that, you eliminate your decision variable in all other constraints, including the objective function. So you're only left with one equation that contains that decision variable. In that equation, all of your other variables are non-basic variables, so they're equal to 0. So it allows you to solve for that decision variable, right? So you remember how we did that? We'd swap it out. It's fairly straightforward. So we were about right here, as I recall. And I said, let's take a look at the new profit equation. And the first profit equation looked like this. Z equals 60x1 plus 30x2 plus 20x3. So in theory, we could increase any decision variable and get an increase in profit. We said, let's pick the one that gives us the most increase in profit and see how much we can actually increase that. And that was constrained by the actual constraints itself. Okay? So if we take a look at our new profit equation, which was just substituting in basically S3 for X3, we swapped out X3 and S3, we find that our new profit equation looks like this. And I ask you guys, what do you notice about it? And one of the first things that jumps out is that our decision variable, X2, and our slack variable, S3, both of them have negative coefficients. So if all these variables have to be greater than 0, we've defined them as being they have to be greater than 0, that means there's really no room for an improvement. If I increase X2 or S3, which I'm not interested in increasing S3, I'm really just interested in my decision variables. But what happens to my profit? It decreases. So this tells me intuitively I don't want to increase X2. So the only room for improvement is X3. If I increase X3, it's going to give me an increase of 5 units, just kind of right off the bat. Now, a question one of you all posed last time was, well, but how does this work? Because you've already used up all your resources in one of your constraints, making X1. Okay? So you can't increase X3, because if you increase X3, you just can't, because it uses one of these resources. And I said, well, this is kind of where the magic of the simplex method comes in. Okay? What it's going to do is automatically decrease, it'll take away an X1 and increase maybe 2 X3s. Okay? And we'll see a little bit how that works in just a moment. Okay? Okay, so here's one thing that I want you to pay special attention to, because this is really the crux of the simplex method. Initially, when you look at a problem like this, like I said, we have an infinite number of solutions, okay? So we were able to take an infinite number of solutions, reduce it down to the number of corner points on the polytope, which is a finite number, okay? Now, so that was a drastic reduction. So in theory, all we would have to do is just figure out where all those corner points are, calculate them all, compare them, okay? There is a fundamental problem with this, though, is because as the number of constraints actually increases, the number of corner point solutions starts to go up dramatically, okay? So let's suppose you have on the order of 100 constraints, okay? Well, if you think about having this polytope, say this cube, and then you take another constraint and you cut it, all right? Then you cut it another way, cut it another way, cut it another way. Imagine that you're cutting kind of facets off the polytope. So it would be kind of like a diamond. You ever see a diamond? And one of the ways that they, promote the value of the diamond is the number of facets it has, the number of faces. So at each face, each facet has essentially, on a diamond, I guess, 3 points on a face. I guess you could have more or less, but let's say 3. So there's a lot of points. So the number of corner points can actually go up significantly, okay? Still a whole lot less than infinity, but maybe more than we want to fool around with computing, all right, especially for very big problems. Now, the simplex method takes advantage of another fact, okay? And this fact, we use something referred to as adjacent corner point solutions. So remember when I talked about basic feasible solutions, I said they're always the corner points on the polytope. Notice how we're only entering one variable at a time, though, okay? If you do this problem, what happens is you only ever swap out one variable with another variable at a time. Maybe x1 with s3, x2 with s4, whatever it may be, but it's always just 1, 1, 1, 1. You never swap out like 3 at a time, okay? Well, because of that, something interesting happens. So x1 was used in the last iteration, and our goal is to try to make all the decision variables basic variables. So we probably want the decision variables to be more than 0 in general, because maybe sometimes not, but in general we're trying to get them greater than 0. So here's a very simple example. We're only changing one variable at a time. So let's take this example. Let's suppose that we're in a 2D coordinate system and we have points xi, yi. Now let's suppose that we start at 0, 0, and we change only one variable, either x or y at a time. All right? So what will happen? Well, let's take and these are just random changes. All right? These numbers don't mean anything. 0, 0, and then I'm going to change the x coordinate. So I'm going to get, say, 2, 0. Then I want to change the y, 2, 4. Then I want to change the x, 7, 4. Then I'm going to change the x again, 9, 4. Then I'm going to change the y, 9, 8. Okay? So if I were to go in and graph these, here's what I get. I get a graph that looks like this, okay? It's just a stair step, okay? But there's something important about this, is if I look at each one of these sequential solutions, they're adjacent to one another, okay? In this case, they can be connected by either a vertical or horizontal line, all right? So I'm kind of stair-stepping my way up. If I were to have changed two variables simultaneously, what would the line have looked like between 2 points? Does anyone know? It'd have been a diagonal, right? But we don't get that. We get the stair step. So if I take a look at our polytope, what happens is by changing only one variable at a time, essentially we move from one corner point solution to an adjacent corner point solution. Okay? So you can't see the interior of this polytope, but the interior of this polytope is at 0, 0. So what's happened is we've moved from 0, 0, which is kind of in the interior somewhere, and we've moved out to this guy right here, get a solution. Then we move to this guy, get a solution. Move to this guy, this guy, this guy, this guy. Okay? So by just examining adjacent corner point solutions, what we have done is drastically reduced the number of evaluations that we have to perform. So if we look at all these points, be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, a few more, say 20, okay? But just from this graph, it looks like that we've only had to evaluate 1, 2, 3, 4, 5. So we've reduced the number of corner point solutions that we have to evaluate drastically. So essentially, the simplex method just walks around the polytope. It kind of walks around these perimeters, the perimeter, these boundaries, until you find the optimal solution. So how do you know you found the optimal solution? Well, knowing how you found the optimal solution turns out to be extremely simple. I'm going to show you guys how to do this. Okay. So once again, we need to enter one of the decision variables as a basic variable. So we know this variable is not going to be x1, all right, because we've already used that one. So we're left with x2 and x3. So if we look at the profit equation, by inspection, we can tell that x3 is the variable that needs to enter. Everyone understand why it's x3? Because it's the only one positive. If you increase x2 or s3, we're not going to increase s3 because it's a slack variable, but we're just looking at x2 and s3. x3, x2, x3. If you look at x2, the coefficient in front of x2 is negative, so you can't increase it. It's already at 0. We've defined it as being a variable that has to be greater than or equal to 0. So it can only go up or stay at 0. So you're better off keeping it at 0 because if it goes up, it's going to decrease your profit. And we're trying to maximize our profit. Okay. Now, the question is, x3, know that. Now we go back to which row should we increase x3 in? okay? I mean x2n. No, x3, I'm sorry, x3, all right? Well, we have to go back in, and this is our new table where we'd substituted all those variables in. Okay, remember doing all that? So we have to go in and say, well, how much can we increase x3? Well, let's go in and take a look at it. Well, if we look at row 1, all right, where did I get these rows? All right, these were easy to come by. All you have to do is plug in the values, your non-basic variables of b and 0. Okay, so let's take row 1. Our non-basic variables are s3, x2, and x3, right? So we're looking at x3. So if we plug in our non-basic variables, okay, of being, let's see, non-basic variables were s3. So this guy's going to cancel out, right? This guy's going to cancel out. This guy's going to cancel out. This guy is going to cancel out. And let's see, where do I got? This guy is going to cancel out. All right? So do you see why those guys canceled out? Because they're defined as non-basic variables. They're zeros. All right? So when I canceled everything out, what I'm ultimately left with in my constraints are these 4 equations. Now I rewrote them, but it's just moving one to one side or the other. So if I look at S1, I say S1 is equal to 16 plus X3. All right? So how much can I increase X3 before S1 becomes negative? No limit, right? This guy can go up forever, and it'll never become negative, all right? How much can I increase x3 in row 2 before s2 becomes negative? 8.
Well, if it's 0, you're going to go ahead and count that.
Yeah, before it comes negative. What'd you say?
It'd have to be greater than 8. Like 0 would be negative.
It'd have to be, the maximum amount that I could increase x3 would be 8. I guess that's the better way to say it. Do you agree with that? I can increase it 7, I'm still okay. Increase it 8, still fine. If I go 8.001, S2 becomes negative, right? But S2 can't become negative. We've already said it has to be positive. How much in row 3? How much can I increase x3? 16. All right, how about row 4? There's no limit, okay? Because x3 is not even included. So the only 2 rows I have to look at, row 2 and row 3. Now remember, we take the smallest value. It's called the ratio test. And the reason why we do it is because this constraint right here kind of becomes a redundant constraint. It's like I said, you got to stay in the United States. You got to stay in Virginia. You got to stay in Tazewell County. All right. Well, if I tell you you have to stay in Tazewell County, I don't need to tell you you have to stay in Virginia, and I don't need to tell you you have to stay in the U.S. All right. Those 2 constraints become redundant. So what happens is row 2 becomes the row where I increase my entering basic variable, which is x3, and I increase it by 8. Okay. All right. So we've already done this. Okay. Now we must choose row 2 to be the row for the entering basic variable because it's the minimum of 8 and 16. So how do we make the coefficient of x3 in row 2 1? All right. So row 2. This guy right here. How do we make this guy 1? We simply multiply the whole equation by 2, right? So if I go back and I look at this equation right here, the coefficient in front of x3 is 0.5, right? But we want to make that coefficient 1. And remember the reason why we want to make that coefficient 1? Because then, once it's 1, you're essentially solving for x3 is equal to whatever, right? I mean, that's the ultimate reason. I mean, if I told you right here, solve for x3, what are you going to do? You're going to move everything over on one side and multiply by 2, right? That's what you're going to do. Because you want the equation to say x3 equals something. Right? So that's why you're trying to get this coefficient equal to 1 in front of x3. All right? Now, you want one row that has x3 in it because that's the row that's going to tell you what x3 is equal to. Now, in all the other rows, what are we trying to do with x3? We're trying to get rid of it, right? So essentially, what you're trying to do is you're trying to say x3 is equal to 8 plus 2x2 minus 2s2 plus 4s3. Agree with that? Now, as soon as I know x3 is equal to this function, equation, what can I do? I can go back to my original table that I had set up, and every time I see an x3, all I do is plug in the expression from row to prime. Right? Everyone understand why I do that? It's just like when you're solving for simultaneous equations and you're using the substitution method. Clear? I mean, we're good on this, right? Now, so how do we do this? Well, I have a handout that I have posted for you guys where I actually do all of this work by hand. Let's see if this one's it. Yep. Okay, so I did all this by hand. Okay, so and that was in row 2, right? Okay, so right here is where you see this guy right here. This is where I multiply times 2, right? And so this is how I get x3 to have a coefficient in front of 1 in front of it. Now, I want to plug this original equation, I want to substitute it in. Anytime I see an x3, I want to plug it back into an x3, right? That's one way to do it. But there's a simpler way to do it. The simpler way to do it is just to take your row, your existing row, say row 0 prime, and I'm simply going to add 2 times row 2 prime. All right, now why do I do that? It's like simply add. What are you talking about? What do you mean? Well, come here, let's take a look at this just a second. Now just hang on because this is important. Let's see. 5. I said 2. I meant to say 5 right here. This guy right here, 5. All right. Now the reason why I do that is because of this. This guy right here. Okay? So if I've got a positive x3 down here that I've multiplied everything by 2, and I want to get rid of x3, then does everyone agree that all I have to do is take this equation right here, the one where I've already multiplied it times 2, multiply it times 5, and add it to this equation, and it'll get rid of x3? Does everyone agree with that? It's just like doing this. The exact same thing. I've got 2x plus 5y is equal to 10. No. say, minus 5y, okay? And then I have 3x plus y is equal to 8. Well, how can I solve this? All I've got to do is multiply this guy times 5 and add the 2, right? You agree with that? And then as soon as I do that, I get a 5y down here. I get a 15x plus 5y is equal to 40. But what happens to my 5y's? Cancel each other out. And then I'm left with 0y. So I can solve this either through substitution or by multiplying and then adding. Right? Everyone remember this. Well, that's all I'm doing here. Okay? That's literally all I'm doing. I'm taking row, to calculate row 0, all right? To calculate row 0, I'm saying let's let row 0 prime, my new row 0, equal to my row 0 prime plus 5 times my row 2 prime, my new row that I calculated. And then when I add them together and I actually do the math, notice how x3 simply disappears. All right? So I had 5x3 right here, negative 5x3 right here, and the two of them simply disappear. And see how I got rid of x3 in my profit equation? Do the same thing for row 1. Row 1 is simply row 2 prime plus row, this should be row 1 prime. Okay? Why? Because I already have a negative x3 in row 1 prime. I have a positive x3 in row 2 double prime. And so these two just cancel each other out. They just cancel each other out. All right? So does everyone see how I'm getting rid of x3 in all of these equations? Is it clear to everyone how I'm methodically going in and getting rid of x3 here, x3 here? I don't want to get rid of it here. I just want to make the coefficient in front of it 1, x3 here, and here I don't even have to worry about it because he doesn't exist. All right? Does that make sense? Wiping x3 out. All right? Now, when I go in and I wipe x3 out, okay, here's what I'm left with. Look, no x3s except right here. So, what are our new non-basic variables? Our new non-basic variables are now S2, S3, and X2, right? Because I swapped these out with my decision variables. So every time we see an S2, let's turn it into a 0. An S2 and S3 are next to. All right, this guy disappears, this guy disappears, this guy disappears. 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 He disappears. He disappears. This guy disappears. So what am I left with? Well, when you reduce it, you're simply left with these equations. Z equals 280. S1 equals 24. X3 equals 8. X1 equals 2, S4 equals 5, right? And all these guys are equal to 0, right? Good? All right. Now, let's go in and take a look at our new profit equation. This is our new profit equation. What do we notice about this profit equation? What do we notice about the coefficients in front of all of our either decision variables or slack variables? They're negative. So what do you think this tells us? Can't go any further. As high as you can get on the mountain. If you increase x2, which is really the only one you're interested in increasing because it's a decision variable, but even the slack variables, theoretically, if you wanted to increase them, what's going to happen to your profit equation? It's going to go down. So this is the criteria for stopping the method. All right? So, and guess what? Here are your answers. So my maximum profit in this model is 280. X1, which is a decision variable, the number of deaths that I'm going to make, is 2. X2, the number of tables I'm going to make, is equal to 0. And X3, the number of chairs I'm going to make, is equal to 8. And these values here, S1, and then S2 and S3, and S4, is how much I have left over. So S1 was equal to what? The number of board feet. So what this tells me is I have 24 board feet left over. S2 and S3 was basically my labor hours, carpentry hours, and finishing hours. I used them all up. S4 was a demand constraint, meaning that, well, I think the most tables I can sell is 5. I didn't sell any tables, so I still have 5 left that I could sell. And that's how we solve this model. Is this clear to everyone? Somewhat? No? What's going on? Is it spring break yet? Do you see how powerful potentially this could be? Like, no, I don't think so. No, this is a very, very powerful technique. I mean, this is what helped win partially World War II, because they would take very large problems, they had limited resources, and say, all right, we expect this return on an investment if we allocate so many tanks, planes, subs, here, 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 here. Where should we allocate them in a way that such that it maximizes or essentially a return on our investment? Okay? And you see it only took 2 iterations to solve this. Your initial solution, your first iteration, your second iteration. So you took a fairly complex model, I mean, you know, an objective function with 4 constraints, and you had, ultimately you end up having what, 8 decision variables, and in 2 iterations, boom, you know. And the reason why is because of the power of this thing walking around the polytope. It just walks around the boundaries, and it doesn't take very long for you to get to the top, the highest elevation. Okay? So this is just showing you the slack variables. If we make 2 desks and 8 tables, we use 28 board feet of lumber. We have a total of 48 available. S1 is equal to 24. So S1, these slack variables, they're not just hanging around. After the problem's over, they end up telling you something. Okay? Finishing hours, we used all of them. Carpentry hours, we used all of them. Demand, we didn't use any of them. We have, you know, all of them left. So I hope you can see that the slack variables aren't just variables we pulled out of the air. Ultimately, we'd like to make all of our slack variables 0, because this means now you're utilizing all of your resources. But this is almost never the case, so then you can kind of do a post hoc analysis and say, well, is there any way we can trade board feet for a few more finishing hours? And you can kind of go in and start reformulating the problem and say, maybe we can even maximize profit a little more, because, you know, if I can trade, because it's ultimately money, 24 board feet, and give myself a few more carpentry hours and a few more finishing hours, maybe I can make an extra chair, an extra table, or something like that. And we'll talk a little bit about that later on in the course. Okay? Now, also remember that we chose the value that gave us the most increase in profit to be our entering value. Remember that? We first chose X1 because it had a 60 in front of it. So the question is, what would happen if we didn't do this? What happened if we just randomly picked an entering variable? And would the method still work? And the answer is yes. Any value will eventually give us the correct answer, but it may not do it in a minimal number of steps. Okay? So it may look something like this. Okay? So you're still going to get to that optimal solution. You'll eventually get there. But it may take a little bit longer because you're not taking the optimal way around the polytope. Now, sometimes the simplex method can get in an endless loop like this. and it just iterates forever. But it is very, 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 very rare in real-world problems, so rare that they don't even usually write error checking into the programs to solve these, because it simply isn't worth it. The probability is like 1 in a quadrillion or something. So it's just not worth wasting computer time to check to see if you're caught in this endless loop. And any example that I've ever seen of this actually had to be artificially constructed by some mathematician just to show it could be done. And the parameters are set such that usually you would never have a problem that would do this. But it is theoretically possible for this to happen. Okay? All right, any questions on this? All right, let me... Okay, this is just kind of a wrap-up slide right here that I want to talk a little bit about, kind of an overview. I'm going to really rush through it because not a lot of value to it. So I think you can see it's unrealistic to solve any practical size problem by hand. All right, so you can imagine if you had 20 decision variables and 20 slack variables. I mean, you're going to be here all day. Well, that's what they used to do. They had whole teams of people on these adding machines, and it may take them 2 or 3 weeks to solve a problem that had 20, 30 variables in it. Okay, but they would actually do that. I mean, now we would laugh at it because your computer could do it in like 2 seconds. So it's a perfect candidate to be solved with the computer. So the question is, how long does it take to find an optimal solution? Before I get into that, I'm going to talk about another method. The simplex method was developed in the 1940s, and there really wasn't much advancement on improving technique until about in the 1980s. And the reason why this came about in the 1980s is that's when researchers started being able to have computers on their desk. Okay, up until that time, if you wanted to work on a computer, you had to go down in the basement of some university or lab and share your time on a huge mainframe. When the 1980s came about with the mini computer and the microcomputer, it allowed you to sit basically in front of your desk and start trying things, okay, and to see if you could come up with more efficient algorithms. So even though by our standards those computers were relatively slow, I mean, you may have been looking at megahertz, maybe even the kilohertz, but still being able to crank out even, say, 1,000 iterations a second, all right, which today we can do 1 trillion iterations a second on very, very fast machines. But 1,000 iterations a second still is pretty fast. I mean, you go through, do 1,000 computations a second, you try something, it takes 5 or 10 minutes, and you come back. Compare it to an existing method that took, say, 15 minutes, and, you do a study, and you say, well, this technique is better. And so operations research went through a lot of new developments in the 1980s because of this fact. Okay, so in 1984 there was a mathematician. He was an Indian mathematician. Narendra Kamarkar was his name, and he developed a new algorithm for linear programming. It was called the interior point method. Okay, and the way the interior point method works is something like this: the simplex would go around like this, where the interior point method would kind of shoot through the middle of this polytope, and it's kind of complex how it works, and I'm not sure. No, it's not that I'm not sure. I don't completely understand how it works. I've never really sat down to take the time to figure it out. But I know it works based on what's referred to as a fine scaling method, meaning that what happens is it takes off in a direction with a guess, and then these kind of constraints in some ways kind of act as it's almost like a force field kind of pushing your solution away from the boundary. So it acts as what's called a penalty function, and then this guy, which would normally keep going straight, he's kind of repelled to go in this direction, So maybe head off up here, and then this guy kind of starts pushing him, and eventually he ends up at the optimal solution. So it's a very in-depth, it's really outside the scope of this class. But it's just a new technique, okay? And a lot of newer algorithms actually use a combination of simplex and interior point method. They both have their advantages. One major disadvantage of the simplex method is as the number of constraints increase, the number of basic feasible solutions increase, okay? So basically it means as you start cutting this, it's like the facets on a diamond, it actually starts, the number of corner point solutions starts increasing. And this can result in a huge number of basic feasible solutions. So it can be shown that the interior point method is what's referred to as a polynomial time algorithm, and the simplex method is known as an exponential time algorithm. And so what does this mean? Well, basically this is what it means. A polynomial is x to the a, and exponential is a to the x. All right? It's like, okay, so what? So if you let x be 2 and a be 3, all right? Well, the polynomial answer is going to give 8. The exponential is going to give 9. Not much difference. Who cares? All right? What happens if you let x be 10 and a be 2? Well, now your polynomial is 100, exponential 1024. So the difference is large. Order of magnitude, factor 10. Well, still not that big a deal in terms of computers, though. Now, if you let x be 100 and a be 2, 100 squared is 10,000. 2 to the 100 is 1.26 times 10 to the 30th power. So that's a big number. Whether you know it or not, we can't even count that high. We have no computers. If you were to take every computer in the world and have it start counting, we couldn't get to that number. Okay? I mean, that's a 1 with 30 zeros. So, it's like, well, I can do a trillion calculations a second. All right, you've only got 1 times 10 to the 18th seconds to go. So you've got what, a billion trillion seconds? So figure how long a billion trillion seconds is. 86,000 seconds in a day. I don't know. A couple billion years maybe. Okay, so now you got a huge difference. All right? So this is why this is important, because when you're dealing with really large problems, the interior point method is a polynomial time algorithm, and the simplex method is an exponential time algorithm. Now, we don't need to know why, but this just represents the worst case of each algorithm. In reality, the simplex usually doesn't follow the worst case. However, for the interior point algorithm, the number of constraints usually doesn't have much of an effect on the number of iterations. Okay? So the interior point method usually doesn't care if you got 10 constraints, 100, 1,000, a million constraints. It only adds a few more iterations. The simplex method is the complete opposite. Okay? So for fairly small problems, the number of iterations needed by an interior point algorithm and simplex, they're somewhat comparable. So for example, problem with 10 functional constraints, roughly 20 iterations would be required for either algorithm. So consequently, on problems of similar size, the total computer time for the interior point algorithm will tend to be many times longer. The reason why is the interior point is much more mathematically intensive. So there's no free lunches. So with the simplex, the math is pretty simple. With the interior point, you got to go in and calculate gradients, kind of vectors, and the mathematics can get difficult. But for large problems, it's actually worth it because the number of iterations is much smaller. Okay? So basically, this kind of an overview. You guys don't really so what on this one. Okay? So why would you go through so much effort to solve complex linear and nonlinear problems? Well, like I said, applications of huge linear programming models sometimes lead to savings of millions of dollars, especially if you're a big company, say like Walmart or an airline industry. So it's worth it. If it wasn't worth it, they wouldn't be hiring teams of people and paying people $100,000 right out of college to go in and work on these problems. I mean, you can easily, you got a degree in OR or concentration in operations research right out of college, easily $90,000. I mean, no sweat. Simply because your salary's worth it, because you're saving the company maybe several millions of dollars a year just by figuring out what the optimal way of doing something is. Okay? Alright, so everyone got this? No questions? You guys are experts, right? The simplex method. Alrighty then. I posted another chapter for you guys. Chapter 4. Chapter 3 really goes in and explains what's going on in the simplex if you're interested. Okay? It really goes on and explains. And I'm just going to give like a 2-minute kind of introduction on what's going on. Here's what's going on. Okay? Let's suppose that we have an equation that says y is equal to 3x plus 4. Alright, what does this equation look like? 1, 2, 3. It goes through here, right? And then it has a slope of 3, which maybe looks something. Is that right? 3x plus 4, 0, xy, yeah. And then it looks something like this. Everyone give that to me? I mean, roughly. That would be the equation of a line. Right? Got that? No sweat. Okay. Now, let me ask you this. What happens if I say, you know what? This origin right here, 0, 0. I want to put my new origin over here at like 5, 2. I want to move this guy right here. Alright, so I don't do anything with the graph. I move the origin. Move my graph. What happens to the equation of this line now on this new coordinate system? Everything changes. Okay? It becomes a new equation. But it's still the same line. It's just you have a new reference. Well, essentially, that is what the simplex method is doing. Okay? You start off at 0, 0, and you've got all of your equations written. They're planes, or n-dimensional planes. Okay? So imagine you got this XYZ, you're at 0, 0, 0, and you got a plane shooting up here, a plane shooting up here, a plane shooting up here. All these planes intersecting each other. But every one of them has an equation associated with it. Now, let's suppose that I take that 0, 0, 0, and I walk down one of the x, y, z axes, because I'm going to be only moving in one axis at a time. And I go to a corner point solution. All right? And I say, I want this to be in my new origin. What's going to happen to the equation of all of those planes? They're going to change. All right? So imagine trying to, right now, if I gave you this problem. I mean, if I gave you this problem, what would you do? Well, I don't know. What would you do? You'd start trying to figure out something, right? I mean, it's like, well, let's see. I think it's going to be crossing up here somewhere. I don't know, somewhere around here, and that's going to give me a new. So my equation is going to be y is mx plus b. So my slope's probably not going to change. So my y-intercept would change. So whatever this is, and you try to figure out a new b or something like that. Or how about if I come in and I say, you know what? Here's what I want to do. I want to move down here at maybe, say, -3, -4. But I want to twist and make my new xy something like this. All right? So not only am I translating my origin, I'm grabbing it, but I'm pulling it down here on the board, and then I'm just going to twist it a little bit. And then I say, go ahead and find the equation for this line on this new coordinate system. Now that would be kind of a disaster, wouldn't it? I mean, it's like, gosh, how do you do that? Well, it turns out it's not hard to do. I don't know how to do it. I've forgotten how to do it. But you can do it. I mean, you can go in and derive it. That's hard. But then when someone gives you the equation, it's like you just plug and chug, okay? Well, essentially, that's what you're doing with the simplex method. You're solving, getting an answer, taking and moving my coordinate system down here and kind of rotating it to fit on one of these new planes, all right? And then you're saying, well, what would all the other equations look like now if I've moved this origin and rotated it a little bit? Well, you know what they would look like? Exactly what the iteration of the simplex method gives you. And that's the magic of it. So instead of you having to figure out, it's like, oh, okay, it's moved here, then I've rotated this way and this way and this way. Just say, let me do an iteration in the simplex method. And those new equations and that second table or that third table or that fourth table are the equations of what happens when you do this. All right? So don't worry too much about hurting your head as to trying to figure it out, but just realize that fundamentally that is what the simplex method is doing. All right? And that's why the guy that invented this was so smart. Okay, so now here's the fourth chapter that I've worked on. And now we're getting into the nitty-gritty. Solving these problems using the computer. Now, there's all kinds of software. There's Excel, CPlex, Lindo, Lingo, QM, OpenOffice is the one I'm going to be using. Probably you guys want to use Excel. Kind of talk about Charles Babbage. He was one of the guys that invented the first computer. Here's an example we worked on in class. I did the graphical method, Eager Beaver woodworking shop. Okay? So, let's take a look and see how we would solve one of these. Okay. Okay, so I know that All right, give me just a moment. Okay, so here's what we have. We have this problem right here, okay? And we want to see how we're going to solve it using the computer, okay? So I have this set up in OpenOffice. You can use Excel. I have no problem with that, okay? So here's what we do. We set decision variables. And I say, okay, my number of chests that I want to build, I'm going to start out at 0. The number of tables I want to build, start out at 0. Now, my profit equation, the way I get my equations is I hit Control tilde, or the number beside of 1 to the left. And that it shows me these equations. So it says this cell, all you guys used Excel, you're all familiar with it. You know how to plug in equations, right? So it says, my profit equation is going to be 2,900 times B4 plus 2,300 times B5. So here's what happens. If I make one chest, boom, I make $2,900. If I make one table, boom, I make $2,300. Okay? So see how this gives me my profit? Now my constraints. I have 180. What did I have 180 of? Was that 180 hours maybe? Can't remember. Let me see, I think I had it up here on my... I think it was 180 hours and 504 board feet. Okay, one or the other. So this is the maximum number I have of each resource. This right here is the amount of resources I'm using. Okay? Everyone got that? Simple equations. So now I want to go in and solve this. So how am I going to do this? I'm going to go up here under Tools. I'm going to go down to Solver. This is also in Excel. It's going to bring up a dialog box for me. It's supposed to bring up a dialog box for me. Oh, down here it is. And it says, okay, what's your target cell? Well, my target cell is this guy right here. It's going to be B8. All right? So I want to maximize him by changing these cells right here. How many tables and how many chests? And then I want to make sure the amount of resources I use, which is these two right here, I just drag, has to be less than or equal to the amount of resources I have. Okay? I go in here under Options. I want to make sure that I have picked OpenOffice Linear Solver. And I'm going to click on Assume Variable as Non-Negative. Okay? Meaning that way I don't have to go in and say x1, x2 greater than or equal to 0. All right? And I hit Solve, and before you can blink your eye, poof. It says, all right, here's your answer. Fill 6 chests, 21 tables, and your maximum profit is going to be $65,700. All right? So all of that simplex method that I went through and showed you guys that quick, OpenOffice or Excel or even Google Docs will do linear problems. Solves it that quick. Okay? So let's go in, and do I have any other problems? Okay, here's the problem I was looking at. The minimization problem. All right? The wildflower example. I think this was in Chapter 1 or Chapter 2. Okay? So the state of Virginia is looking at putting wildflowers on the side of the road. Okay, they have a zebra mix and a leopard mix, and it costs $100 a bag for the zebra mix, $50 a bag for the leopard mix. And I want to make sure that I have at least 1,800 pounds of zebra mix. Is that right? Let me see. I need to go in and look at these problems and see exactly what it's telling me. Let me open up chapter. What is this? Chapter 1, maybe? Surely it wasn't Chapter 1. I think it was Chapter 1. I don't think it was Chapter 1. Maybe it's Chapter 4. But anyway, forgot what my constraints were. And anyway, this is a minimization problem. I'll get back with you on that. And essentially, instead of maximizing, we are just looking at minimizing. So we go in, we say, okay, our target cell is going to be our profit. We want to minimize these two right here, and we want to make sure B11, these have to be greater than, equal. Hit Solve, and, well, I'd already solved it. Let's try it again. Solve. It says, all right, you need 30 bags of leopard mix and 40 bags of zebra mix. And your maximum profit's $5,000, and you were able to meet these constraints. Okay, so we'll go over some more problems on Thursday. I'll post some homework. You guys see where we're going with this? So I'm hoping to make the transition. It's kind of been a long, hard ride so far, kind of digging through the fundamentals. But then, right about now, the course kind of changes direction to where I'm not so interested in you guys being able to sit down doing these problems by hand. I'm more interested in you knowing how to formulate them to be able to solve them on the computer. All righty? All right, see you guys on Thursday then. And don't forget, for you guys that came in late, Thursday I'm going to be going over homework that I will post today, and next Tuesday we will have an exam. Okay? And I'll give you more details on that Thursday. All righty?